Hey guys, welcome to another Pymunk tutorial, and today we'll be doing a simulation of, well, kind of what you've been seeing on the news lately of flattening the curve and the coronavirus and the spread of this. I'm no epidemiologist, but I want to kind of give you a sense of how to make this from a programming standpoint. So right here we have white, which is not infected, red, which is infected, and blue, as you can see, which is recovered. And we'll do graphs like this, where we have a non-social distance and a social distance, and we'll talk about what the meaning of that is later on. So we'll get started with the same setup as we had in the Pygame Basics playlist of the setting up the display video, and I'll link that below in the description. But definitely review that, because I probably won't be reviewing exactly what each of these are doing here, because I've already done that in the other video. But if I run this, I go ahead and I get this empty display. So we're going to start with the empty display. We're going to do all the display stuff, and then we'll add the Pymunk physics to it, and then we'll make the graphs. So let's get started. So as I've done in the past, anytime I'm creating an object onto a Pygame screen, I always make it its own class. I think this is the best way of organizing it. So I'm going to create a class called ball, which is going to represent each of our people in our simulation. And each class requires an init method. And within the arguments of the init method, I want to think what's going to be different when I initialize each instance of a ball. Well, its x position is going to be different, and its y position is going to be different, right? So let's go ahead and save this as self variables. So self.x, self.y equals x and y. And then within this class, we also want a method to draw the ball. And so we're going to use the Pygame function, pygame.draw.circle. And then you've guessed it, this draws a circle. So if I remember right, which is a big if, the arguments here will be the display color. So for now, we'll do white. So it wants an RGB triplet, so 255, 255, 255, which is going to be our white. And then I believe it wants our position. So a tuple of self.x, self.y. And the last thing it will want in this function is the radius. And to know what these arguments need to be per the function, you can look at the documentation, which is also in the description of Pygame. And of course, I'm going to have to bring in self into this draw method here. And okay, so whenever I'm making multiple, just like we did in the Pong video, I think making multiple instances of one object, the best place to do it is create a list here before we get into the game loop. And I'm going to call it balls. And let's say ball of, and I'm going to come back to the x and y position. So I'll just say, I'll leave it blank for now. For I in range, how many you guys want? Let's do 300 balls. Okay, so for the x and y positions to start for each of the balls, I think it's best to do a random x and a random y within the screen. So if you look up here, I'm running this display of 800 pixels x and 800 pixels y. So that's the size of our display. So we should have a random x and y position within that. And so to do anything random in Python, we need to import the random module. And for our x, we'll say random.randint. So randint gives a random integer between 2 points, and we do want an integer for our starting position because Pygame only understands integer values. So we'll say 0 and 800 because it's the display has 800 pixels in x, like we talked about. And then same thing in y because the display also has 800 pixels in y. So now we have a list that contains all our ball instances, and of course we want to draw them. So I'll say for ball in balls, ball.draw. And then of course, every time the screen refreshes, remember that's what the game loop is. It refreshes the screen for as many frames per second as we give it down here. Every time the frame refreshes, we want to re-update the screen. So we want to refill the background. So we say display.fill. With what color? Since we're doing the balls as white, we probably should do the background as black. And so I'm giving it a tuple of 000, RGB. So let's go ahead and run this and see what happens. Okay, great. So we have a bunch of random balls in random positions. You can see that some of them, because we have the centers to be anywhere from 0 to 800, some of them are going to be a little bit off the edge, but we'll focus on that later. But this is exactly what we want for our display. Now, to get these balls moving, we're going to use our physics engine Pymunk. So let's go ahead and talk about how to incorporate Pymunk into this. First things first, let's import Pymunk. Now, Pymunk has what's called a simulation space. And again, we talk about a lot of this in the Pong videos, but I'm going to go over it again here. So Pymunk has what's called a simulation space, and we're going to create an instance of the space object, and we're going to call it space. And what this is it's a simulation space where you add all your bodies and shapes, and we'll talk about what bodies and shapes are in a second. And everything that's in here contributes to that physics simulation. So this is an object that kind of contains all the physics that is going on in our simulation space. So our goal is to add, anytime we create an instance of this ball, that we want to be adding that to the simulation space. So to do that, we need to create first a body, which is in Pymunk is a point-like object. So point-like physics object. So what are some things that we need to do with a point-like object? Well, we need to give it a position. Self.body.position equals x and y. And at this point, we can get rid of these because we won't be using it here, as you'll see, but I'll wait on that. And then we probably should give it a velocity as well, .velocity. And I'm going to use randomness again here. So I'm going to say random.uniform. So the difference between random and random.uniform is random.uniform chooses any floating point numbers between a and b, while randint will choose a random integer between a and b. And for the case of Pymunk, we don't really care if our values end up being floating point numbers because it can handle that. So I think a good one is -100 and +100. So what the absolute value of 100 means when it comes to velocities is 100 frames for every second of simulation space that we pass. And we can choose later how many seconds we want to pass per frame, which will, as you can probably imagine, will correspond to the frames per second. So 1 over the frames per second is what I think is a good value to pass per frame. But just know that the absolute value of this velocity is going to depend, or how much that absolute value of the velocity actually affects the physics simulation is going to depend on your simulation step, which we're going to make dependent on your frames per second. So I wouldn't worry about it too much. Just pick a value and just kind of go with it when we set the body's velocity. And a lot of this is going to make more sense when we start actually running it. And so for y, right, so this is our x value for velocity and our y value for velocity. I think I can just keep it at the same thing, and we'll see if this looks good later. Okay, so whenever we're adding things to the physics engine, to our simulation space, we need to do two things. Create the body, which we have, which is our point-like object. And we also need to give it a shape. And there's a couple different shapes in Pymunk that are built in, but I'll use circle. And what the shape is it defines how the collision dynamics occur to the body. So the body is point-like, but it doesn't have any sense of what is the collision shape around it. So should I collide with other objects like a circle, like a square, etc. So we're going to say a circle, and it needs the body to be attached, right? It wants a radius of its circle, so we can kind of get a sense of size. I'll use the same thing that we draw it at, which is 10. And the offset would be if we want the circle shape, the center of the circle to be different than the center of the body, which is the point-like object. And I mean, we don't, so we can leave it at that, which is 0, 0. And then the last thing we have to do, or actually before that, we should identify some characteristics of the shape itself. So remember, the shape is the collision body, and what are some things that the collision body would need to know? It would need to know the density. And I'm going to set the density to be some arbitrary value 1, just because we're only going to have balls colliding with each other and maybe some walls. And so it really doesn't matter what the density that we set it at, because they're all going to end up being the same. And so they're all going to collide in the same way. But you do need to set it, otherwise the physics simulation kind of does some funky things. And then we want to set an elasticity, because we want all of our collisions, elasticity. Sorry, it should be shape.elasticity because it's within the shape. All of our collisions are going to be elastic collisions. And to do that, we can set the elasticity of all of the objects as 1. And then the last thing we do here is we want to actually add these bodies and the shape to the physics simulation. So to do that, it's space.add, and we want to add the body, and we want to add the shape. So that might kind of come off as a lot, and I think it'll get easier as you do this more and you make more games and you make more classes and you kind of get in the habit of create the body, create the position velocity, create the shape, and add them to the space. You'll just kind of get the sense of it a lot better. But yeah, I know in the beginning that's a lot. So continue to follow along and we'll figure this out. So anything else we need to do? Okay, so whenever we run the screen and we refresh per frame rate, we want to also pass the simulation a little bit and kind of let the physics go on, let the time go on within the physics simulation. So to do that, it's called space.step is the function, and then a dt, so a delta time, so time for each simulation step. And I think it makes sense to do that at 1 frames per second just to match the physics simulation. Do you have to? Not really, but I think this way, if you change the frames per second, then you're automatically changing the physics simulation and you won't see a difference in the velocities of the objects. So let's go ahead and run this right now. And we have nothing that moves. So, okay, let's understand why nothing is moving. So we'll look at where the objects are being drawn. And they're being drawn at self.x, self.y, which is only the initial x and y, not the current position that this physics simulation within Pymunk is telling it. So we need to obviously change that. So to change that, I'm going to say self.body.position, or at least I want to say that. But for those of you guys who are paying very close attention, you're going to say there's a problem here. So I mentioned before, Pymunk. So as I mentioned before, Pymunk does not care about floating point numbers. It can handle it just fine, while Pygame cannot. And since we're giving it a random floating point number here, and we're giving it a random floating point number step, we're going to get a floating point number for the position, even if we start off with an integer. So the moment this ball moves, it's going to toss a floating point number here for x and y, and it's going to throw an error. So instead of this, we need to set this x and y position to be an integer every frame. So I think the easiest way to do that is use tuple unpacking. And instead of passing the position, we'll pass int x, int y. And then remember, this has to be passed not as two separate arguments, but a tuple. So there we go. Now let's go ahead and run this and see where we're at. So we have a bunch of balls. They're colliding with each other. They're moving around great. They are moving off the screen, which is not behavior that we want. So one thing we could do is we can create artificial walls up here where the display is. And we don't even have to display the walls, so that way it just kind of look like it's bouncing off the side of the display. And that way all the balls will stay within the display. So let's go ahead and do that. So again, anytime we're making an object, we want to make a class. So I'm going to say class wall. And then we want an init method, always, right? Always self. And then what is going to be different between every instance that we create this wall? Well, a P1, which I'm going to say is point 1, which is one endpoint of the wall or segment. Point 2, which is the second endpoint. So those are what's going to be different between all of the walls that we create. So we're going to create 4 walls, top, bottom, left, right. So let's create the body, self.body. Again, this is all the same. However, as you see here, we're gonna have to set a body type. So there's 2 different body types in Pymunk. There's a dynamic, which is what it's assumed to be used, which is what we used up here in ball. The dynamic body type means that the body that we create is going to contribute to the physics engine. It's going to collide normally. I guess all of them contribute to the physics engine, but this is going to collide normally. It's going to move around based on the velocity that we give it. It's going to calculate its own collision dynamics. It's going to pretty much do all the physics. And then there's this second type, which is a static body. A static body contributes to the physics environment, but it just stays still. It doesn't get affected by other objects. So it's like kind of like a wall or a floor where if it gets hit, it doesn't take some of that momentum and move itself. It just stays still. So you can kind of, the analogy there is you can think of it as an infinite mass or an infinite density object, but it doesn't pass its momentum to another object. And then there's the last type, last body type, which is a kinematic body. A kinematic body is similar to a static body with everything I just said. However, we can set a velocity to this. So this might seem kind of silly, but I think the best example is, again, going back to my Pong game, the players, which is just the Pong paddle, should not be going around in circles, or should not be affected by the ball, and should not be given a torque or a momentum or anything like that unless I press a button and I give it a velocity. So that's kind of what you use a kinematic body for. So for the walls, we're going to want a static body. And to set a static body, we'll say body type equals Pymunk.body dot, and then all caps, static. The other difference that we're going to get, and I'll show you this later, is since this is a static body, the body itself should not be moving, so no position. Well, there should be a position, but no velocity. And so we don't have to add it to the space. So we'll just say space.add self.shape. And I'll show you that when we get there. But right now, let's create the shape. So self.shape. So for walls and stuff, I like to use segment, which is exactly what you think of. It's a line segment. It wants a body attached to it, always. An A, which is our first point. A B, which is our second point. And a radius, and in this case, for a segment, the radius means the thickness. So I'm just going to use a thickness of 5. Something I've noticed in Pymunk, but you have to be a little careful of, is sometimes when you have a segment and you have, let's say, a ball or a circle, I should say, for Pymunk, and it's moving past the segment, you would think if it's a static body that it would just bounce off. But if this thing is big enough, if the other object's big enough and it's moving fast enough, sometimes there's a glitch in the physics engine where it just kind of moves to the other side of the static body. So it kind of goes through the wall or through the floor. And so sometimes you just have to make your thickness of the segment big enough so you can think of it as being strong enough to handle the physics engine, I guess. But I don't think this is going to be a problem here. But if it is, then we'll change it when we come back. So things you may be wondering, why didn't we set a position for the body? We kind of did. So remember here I talked about the offset to the position that we did for shape. This is essentially what we're doing here. I just think it makes a little more sense than to set the body's position because of the way position is defined for a segment, which is 2 points instead of an X and Y sort of center of a circle. If the body was moving, so for a kinematic body, this may end up being kind of an interesting and a relevant distinction. But for a static body, you're not going to even notice the difference. So technically the body's position here is 0, 0, and the offset for the collision information is P1, P2, but there's no difference between having the positions be P1 and P2. I guess position will be 1 point, so it'll be the center point, and have the offsets be offset to that. It really doesn't matter. Okay, so we need to set we don't need to set a density for this shape because it's an assumed infinite density when I say static body, but we will need to set an elasticity. So let's go ahead and do that to be 1 for elastic collisions. And then we need to add, remember, just the shape to the space. So self.shape. Do we want to create a draw class? Or sorry, a draw method? No, we don't. We don't really need to draw this onto the space or onto the Pygame display. So I'm going to go walls because we're going to have multiple, and this is where we put multiple instances of one object. And we'll create the first wall. So we need a P1 and P2. I'll say 0, 0. And remember, each of these points are going to be its own tuple. So this is going to be kind of a tuple of tuples. So keep that in mind. And then we'll do 0, 800. So remember, it's X, Y. So the second point is going to be the Y. So this would be the left wall. Right? And then we want to create, let's go, let me just make sure I did that right. I did not. Yeah, so be careful here because we want to create another element to this overall list of walls. So wall of, let's go 0, 0. And then let's do 800, 0. Right, so this will be the top. And then we'll do another one. Wall 0, 0. Sorry, wait, this will have to be 0, 800, let's do. And then I guess 800, 800. And then the last one is going to be 800, 0. And then 800, 800. Now, do I have to say for wall and walls, wall.draw? No, absolutely not, because we're not drawing this onto the screen. In fact, if we tried that, it'll just say that there's no draw method. Okay. Will this contribute to the physics simulation, though, the walls? if we don't draw it? Yes, because drawing has to do with Pygame. Pymunk will already consider it because we've added it to the Pymunk space. So let's go ahead and run this. And now the balls are bouncing off the walls of the display. Now, if you really look closely, it is bouncing a little bit early. And that's because the thickness we give it 5 is 5 pixels, and it's not exactly on the edge. If you cared, you can totally kind of adjust each one of these positions to make it bounce exactly on the edge of the display. I don't. And then the other problem that's been fixed is if the balls have started off the display, Pymunk is correcting the balls on the first simulation step to get back into the display. So that kind of takes care of that physics idea of like overlapping objects for us. So all this is great, but none of these are infected. So let's start creating the mechanism of infection and getting infected. So to do that, we'll go back to our ball class. And I think it's a good idea to make a method called, I don't know, infect, I guess. And what should happen when we have a ball that's infected? Well, it should be red. Right now, everything's drawn as white. And so I think it's good to create, let's say, another attribute called infected. So be careful not to use infect because we use that for the method. Equals false to start. And then if this infect method is run, we can set self.infected to be true. And then here in draw, we can say if self.infected. So if we are infected, then we don't want to draw in white, we want to draw in black. So I'm going to use copy and paste. That wasn't copy and paste. Now I'll use copy and paste. And so it's RGB in the color argument. So R is red, G 0, B 0. And then if not infected, so otherwise, else in Python, keep it as white. So let's go ahead and run this. Of course, we didn't tell any of these balls to be infected because they all start off false, not infected. So none of these are going to be red just yet. So we should infect at least one person, one ball before we start. So after I create the balls, I want to infect a random element from this list, and I want to run its infect method to infect it. So I can say random.choice. So random.choice chooses a random element from a list or any sequence, I guess. Balls.infect. And so it's going to run a random balls infect method. So I run this, and that one was our lucky winner. And it set self.infected to be true, which means it's drawing is red for now. Now we want to make the mechanism of this infected ball infect other balls. And here's where we have to start recording the collision information and collision dynamics between the two balls and between all of the balls. So now is when we have to start recording the collision dynamics between the balls. So in Pymunk, to do that, we can use what are called collision handlers. Essentially, collision handlers mean that you have two objects that we set with an identifier integer. So we'll set one to be like, let's say 1, another one to be 2. So if 1 and 2 collide, the collision handler will tell it what to do when 1 and 2 collide, for instance. So again, a lot of this is easier by example. So let's just start doing it. So we have how many balls? We have 300. Well, I want to create this as a variable for now. So maybe I'll call it, let's say population. In fact, I'll do it all the way up here. Population equals 300. And then what can we do? So we want to make a different collision handler identifier. So an integer for each one of these balls. So I can kind of differentiate them by integer, kind of give them an identifier number. So I'll say for I in range, and I'm just going to tell you right now, 0 as a collision handler identifier sometimes just does not work well with Pymunk. So I want to start it at 1. And so to start at 1, we want to say 1, and we want to go up to population, but since we have a soft stop at population in Python, we have to say population plus 1. So now this gives us the range between 1 and 300, literally the number 300. Well, if we did just one population, it'd be 1 and 299, and we won't have enough to go through the whole balls list. And so to set the collision identifier, you have a attribute within the shape attribute within the ball class. So it would be balls of I. So to get the ball object from the balls class, dot shape dot, I believe it's collision type is the name of the collision handler. And so I'll set it as I. So the first ball in this list, wherever it ends up being in a random position, will get the identifier 1. The second will get 2. The third will get 3, and so on and so forth. However, we want that to contrast between an infected ball. So anytime that we are infected, we want to hold different values so we can kind of tell if one of those balls collides with the infected one. So I can say here, we're going to change the identifier, the collision type, to, let's do population plus 1, because we want to make sure we don't accidentally overuse a value, an integer. But if we do population plus 1, we know we're never going to get there. And I think eventually I'm going to make a playlist that kind of goes over the basics of Pymunk a lot slower and a lot more clearer than this. So keep an eye out for that. So now we set the collision types, but we haven't told the computer what to do whenever we have two things that collide. So we're going to go ahead and do that by creating what are called collision handlers. So to do that, we have to add them to the space. So we'll say space.add collision handler between, let's say, I, which is the current ball within this loop that we're looking at, and any infected balls, which has a collision handler of population plus 1. And now to tell this collision, first we have to, I should actually identify this. Let's identify it as handler. That's definitely not how you spell it, handler. Now to tell the handler what to do when these two things collide, there are 4 different functions, or 4 different, I guess they're methods of the handler object that we could use. There's the begin, which means what to do when two objects begin to collide. There's pre-solve, which means what to do right before we solve for the collision. There's post-solve, which means what to do after the collision dynamics are solved. And then there's separate, which is what to do after the balls have separated. For our case, it literally doesn't matter which one we use because it's going to be like 1 frame difference. So I'll just use, I guess, separate, handler dot separate. So when the balls have finished colliding and they've separated from each other, we want to do something. So pass a function here to do something. And what we want to pass is this balls I dot infect. We want to infect that exact ball that has this collision type I. So again, if you guys might be sitting there wondering, why don't we just use 1 collision type? So I guess 1 for all the non-infected balls and 2 for all the infected balls. Well, this is the problem here, is what would be passed to the collision handler. If we pass a generic sort of infect class method, then it would infect all the balls if one of them hits an infected ball, which we don't want. So this is the best way I can think of how to do this. And if you think of any better ways, please let me know in the comments. So let's see, are we completely set? Okay, we're not, because one thing that we should know, and it's a little strange, but one thing that we should know about using any of the collision handler methods is it's going to pass 3 arguments to whatever function we give here. They're called, and I'm going to put it up here because if we don't have it here, it's going to complain, it's going to throw an error that we don't have these as arguments. It's called space arbiter data. Now again, what do I call these? Doesn't actually matter. I can say ABC for all I care here, but I won't. And I'm going to set some default values so that way if I'm too lazy to ever put it in the future, I won't. So Pymunk's going to add these arguments behind the scenes for separate. So that's why we really need it there. And this should work. So let's go ahead and run this. Of course not. So list index out of range. And let's see what happened here. Okay, so if I'm going to run I from 1 to population plus 1, I'm going to get in the last value 300 for I. However, indexing wise, I want to keep it 1 less than that, from 0 to population. So I'm just going to go, for indexing sake, balls I minus 1. So that way the first one's going to be the 0th index, which is what we want. Second one will be the 1th index, which is the second element, which is what we want, and so on and so forth. So let's go ahead and run this. And we still have a list index out of range because I didn't do it in every place. I just did it in 1. So again, it's probably not the best way of handling it, but here we are. And let's go ahead and look at this. So we're infecting on every contact. We're infecting. And there it is. We've infected everybody. But nobody's recovering. So our next step now is to write the recovery mechanism. So to do this, we need a sense of how long has the ball been infected, and then just set a sort of timer as to when that recovery would happen. So I'll say, let's go recovery time, and this is going to be in frames, and I think let's do about 300. And again, this is going to be dependent on this frames per second. So maybe if you wanted to do, so I'll say dependent on FPS. So if you want to do something like FPS times 3, so that way if you ever wanted to change the frames per second, you can without having to go back and change some of this stuff, but I'm not going to. But I'll leave this comment there so you remember that. And so what we want to do is sort of pass time within this ball class. So I could say define pass time as a method, bring in self, and say if self.infected, right, then we want to increment a timer. And if that timer gets to recovery time, then we want to say we've recovered. So we're going to start having to add some stuff here. So I'll say self dot, I've already used recovery time, so I guess self dot infected time as a name. And start off as 0 because we're not infected yet. If self dot infected, so if we become infected, then we want to increment self dot infected time plus equals 1 plus equals 1. And again, we're going to run this method every frame. And then I can say if self.infected time is less than or equal to the, greater than or equal to the recovery time. And again, we could probably do just equal to the recovery time. So if this infected time gets up to the recovery time, then we'll do something. And if we write this code right, it'll never go over. So we don't need to do greater than or equal, but it doesn't hurt. Then what do we want to do? We want to set another flag called, I guess, recovered. And then, of course, we're going to start off at false. And we want to do two things. We want to first set infected to false because we're no longer infected. But second, we want to recover. So say recovered true. Okay. Now, in regards to draw, I want to draw recovered things as blue, I guess. So elif self.recovered. So here we have if self.infected, do this. Else if, or elif in Python, recovered, copy and paste. Change the RGB, not R is 0, G is 0, B will do 255. And now all we have to do is make sure we run this pastime function for each ball within the game loop, so each frame. So since we're already looping through each frame because we have to draw, we can go ahead and go ball.pastime as well. And let's run this and see where we're at. So we're infecting, and now we're recovering. And if you look real closely, I don't think you can really see it, but if a recovered ball hits a non-recovered ball, so let's go run this again so we can get that scenario here. As of now, it's still, I don't know if we're going to get that scenario, but as of now, it's still going to infect, and that's not the behavior we want. The reason being is we've changed the infected ball's collision type to be the infected one when it got infected, but we never changed it back when it was recovered. So we're going to have to do that here, and we'll do that here, which is where the moment it recovers, right? So I'll say self.shape.collision type. And what collision type do we want? Well, it's a little complicated to try to recover the old collision type. I guess we could always pass in a value here, do some dependency injection. Again, too complicated. At the end of the day, we don't actually care what the collision type is anymore because we don't care if a recovered person collides with an infected one or a non-infected one. So I can do something random. So I'll do population plus 2 just because I know I'm going to avoid hitting another value, but it really wouldn't matter in this case at all what I put here, as long as I'm not in population plus 1, which is the infected one. All right. Okay, so let's go ahead and run this. Again, this shouldn't have changed anything. I don't even know if we're going to get this scenario where an infected or a recovered person hits a non-recovered or a non ever infected in the first place. But you have the full simulation now. The last thing we want to do is make our graphs. So to make graphs in Python, the best way is using matplotlib. And maybe in the future, I will make a tutorial on matplotlib. And if you guys are well versed with matplotlib, you guys are going to be screaming at me right now because I'm not going to use the object-oriented way of making plots, which is the recommended one. I just think it's a little bit too much for a simple tutorial like this. We're just going to use a straight up function plot, which just takes two arguments, x and y, and then the third to kind of determine how you want the visual of the graph points to look like, and then it just graphs it. Pretty simple, kind of rough and quick. So within this loop, we want to first get a list that tells us how many people have the virus, right? Infected, sort of an infected amount, and then a recovered if we really want. I guess we're not going to do the recovered graph because I don't think it'll be super interesting, but we will make a list for infected people. So I guess I'll do this here again because this is right before I enter the game loop, and I'll say infected count, I guess, as an empty list, and I'm just going to append through every frame. So to get this, we need to loop through all the balls and determine how many of them are infected. And luckily, again, we're already looping through all the balls. So I can say infected count this frame. I just don't want to use the same thing, same name as the list here. This frame start at 0. And then just use some copy and paste. And I'll say if ball.infected. So this is where we're using another way of using this attribute, not just in the draw method, but if ball.infected, then infected count this frame plus equals 1. And at the end here, we can say infected count dot append infected count this frame. So let's go ahead and look again at what we just did. So I'm creating an overall list when I start the simulation that's empty. And each frame, so in this while loop, each frame, we're going to start a count at 0. And as we loop through the balls, we're just going to count up how many of them are infected. And we're going to append that value each frame to infected count. Now, one thing I do want to be careful of is as the frames go by. So in 1 second, we're running this at 90 frames per second. In 1 second, the size of this list is already going to be 90. All right. In 10 seconds, the size of this list is going to be 900. In 100 seconds, which is 2 minutes, which I may talk for 2 minutes while I learn the simulation, we get into 9,000. So I do want to cap the size of this list. 9,000 is not a lot, but in general, I think it's a good idea to cap the size of this list so we don't overwork our memory. So I'll say if length of infected count is less than or equal to, I guess 1,000 is probably good enough, then do this. Otherwise, let's just not, because by 1,000, I'm assuming everyone's going to get infected already, so the graph won't even be interesting. And also, it's just a good thing to cap this off so we don't make this list too big. And again, there's probably a better way of doing all of this, but this is the tutorial you guys got. So let's go with this. And so the last thing I want to do is after the pygame.quit. So after we quit the simulation, and this is very important because pygame.quit, Pygame uses matplotlib behind the scenes. And if you ran this before and tried to plot before, when I run pygame.quit, it's going to quit matplotlib and it's going to kind of not respond. We'll go matplotlib. What did we import it as? We imported it as the straight up thing. I'm actually going to import it as plt to make it easier to type. And I go plt.plot. And now we need an x and a y on this graph. So the y is going to be our infected count. And I just realized the problem here is if I start this infected count within the function, it's going to stay local within this function. So I can say global here, or I can just start this infected count outside the function. And because it's immutable, because it's a mutable object, then by changing within the function, we're going to change the global variable of the infected count as well, and we'll be just fine, and we can do that. So infected count is fine, but what are we going to do for our x? Well, we want it to run from a range of start at, let's say, I guess 0 is fine, to the length of infected count, right? and step size of 1. I don't have to put that, but I will. I actually don't have to put the 0 here as well, but just to kind of spell it out. So this will kind of give us a x-axis of 1, 2, or 0, 1, 2, 3, 4, 5, 6, all the way up to the number of frames that we've run to infected count, which if we leave it forever will be 1,000. If you want something smarter than that, then you guys can change that, but I don't. So let's go ahead and run this. Let's watch the simulation run for a second. Again, we have our white, which is our uninfected, and we see some massive population spread, and we see some massive recovery. And we're done. So if I X this out, then this runs, and we've created our first plot. Now, how can we simulate some type of social distancing? And this is where, there's a whole field of epidemiology that I'm not well versed in. And I'm just giving you a framework to do your epidemiology studies. But here's an idea. What if when an object is infected, it stays still? So if a person is infected, it just doesn't move anywhere. I guess it can still be collided with other things, but we want it just to stay still if infected. So where can we put that? I guess the best place is under infect. We want to stop the person when it's infected. So I'll say self.body.velocity equals 0, 0. And I also wanted to kind of have a little bit of ability to not be pushed around by other objects. Otherwise, then there's no point in stopping the velocity, because then the velocity is just going to be reset when it collides with another object. So to do that, we can just up its density, because so all the other non-infected people have a density of 1. So I'm just going to set this density to be kind of high. So now all infected objects should pretty much stay still. So let's go ahead and see what the behavior is. So yeah, we got infected, we stay still. Some of us recover, and we'll see where we go. And a lot of us are recovering. And let's see if we can recover before we infect everyone. Oh, we're getting so close. Oh, isn't this sort of model the frustration of what's going on right now in real life so well? Yeah, like right when we feel like we got it under control, we're going to, this might take a while, by the way. So how long are we allowed to kind of take here? Well, we set the limit at, I think, 1,000 for the, oh, yeah, there we go. And so I think that'll be 1,000 divided by 990, so a little more than like 10 seconds we can go for the graph. And yeah, so that's what happened here. We kind of stopped too early with the graph. So I'm gonna kind of allow this to run a little longer. So then instead of 10, we'll do 10,000. So do you guys see what was happening here? Our infected count was running out of time before it stopped recording. So let's go ahead and do that. So this will give us 100 seconds, which is about 2 minutes. And hopefully this happens before 2 minutes. Oh, this might happen. Ooh. So here we have, oh, okay, we're done. So that happened because our random person started off on like a corner somewhere. And our graph looks funky because there were only like 3 people that ever get infected at a time, which we want a little more than that. And so we want kind of greater community spread, so we could change the velocity, but I'm actually just going to keep it and see what happens. So to make the two sort of graphs in the same graph as I showed you guys in my thumbnail, what I will do is I will stop social distancing by commenting out the change in velocity and density. I'll go ahead and run this and let the world get infected and create one graph. So that's going to be our first graph. And wow, this happens fast. Oh, wow. Check this out. A few people never got infected. Those guys. And so if I stop this, now I've created this graph. If I don't X this out and I run this again, Matplotlib is smart enough to just pin the next graph onto the same graph here with the same axes. So let's go ahead and now reactivate our social distancing. And let's run this. Where we are. Oh, we're in the corner again. Let's see if we can infect a bunch of people though this time. Yeah, we are getting there. I think we will. Our recovery time is really fast. Maybe I should slow that down a little bit. And we're getting there, Okay. Almost there. I wonder what parameters I used for the beginning of this video. because that one looked really good. I'll have to look at it, but that's okay. Oh, right when we thought we cured coronavirus here up top. Right when we, oh, again, right when we think we're recovering. Come on, recover. Last guy. Yeah. Okay, now if I X this out, it'll draw this on the same graph, and we've significantly flattened the curve here. Now this is a way exaggeration. One thing I can do is maybe reduce this recovery time to say 160 and then run this again. And so let's go ahead and run this one more time just to kind of show you. And I guess a lot of this is luck, right? You just find a random location, and you can take whatever epidemiology conclusions out of what I just said. But so let's see what that graph looks like. So the third graph looks, I guess, flat, less flat in the beginning actually, but that dropped off pretty quickly because by random luck there was nobody around. But anyway, this is sort of how to make the framework. I recommend trying much more clever things than just stopping right here. Maybe take a few frames for asymptomatic, and then when you get symptomatic, then quarantine by taking you off the screen. Try out different things. I've given you the framework, and let me know if you've done anything interesting.